All right, we now come to the part that I would say, I'm not sure I can offer good reason, but I would say it's my favorite part of this entire semester. We're going to look now at the all pairs shortest path problem and how this can be given a linear algebra kind of flavor. It's very reminiscent of linear algebra, but it's not quite linear algebra. It's piecewise linear algebra or nonlinear algebra, actually. All right, so I will start by example. Let's consider this graph here. We have 4 nodes, A, B, C, D, and we have I have an undirected edge-weighted graph, and I have some costs for transitioning from one node to another. In this case, I have no connection between A and D, and because I have no connection between A and D, I'm going to associate with this edge a cost of infinity. Now, I want to argue that if we want to look at the standard shortest path problem, we can solve this problem where all pairs shortest path means I want to know from each node to every other node what's the cost of the shortest path by some kind of matrix multiplication, a generalized kind of matrix multiplication. So to remind you, or not to remind you even, but just to say why I call this matrix multiplication. In ordinary matrix multiplication, so what we have here is some matrix C, and and C is a product of 2 matrices A and B. And well, I take the inner product between this row, let's say, and this column, and that gives me this particular element of my matrix C. And as I go along this row and as I go along this column, I'm using the index K, and this is the formula that you see on the left. Okay, just standard matrix multiplication. And I've highlighted in 2 colors. There's a summation, the green thing, and there's a product, the red thing, which is why this is also called a matrix product in the sum product semi-ring. Now let's try out something and replace these 2 operations. So I'm going to replace the sum by the min. I'm going to replace the product by addition. And well, if I previously called this sum product, then this time I'm going to call it a min sum operator. And let's try this out. So in the graph, in the example that we've seen above, I've just replicated here, I've just copied from further up this matrix. This matrix had the cost of going from one node to any other by at most 1 hop. So 1 hop, I mean 1 step of walking along this graph. I've just copied this matrix. Now let's do this kind of funny matrix multiplication. Yeah? So in particular, let's look perhaps at this element here. So I have 0, 7, 1, and infinity. And okay, maybe I should, because I said earlier product before, let me write this more like a vector. 0, 7, 1, and infinity. And here I have 7, 0, 5, and 1. All right. Now, in an ordinary sum product sense, what I would now do is I would multiply the 0 with the 7, I would multiply the 7 with the 0, multiply the 1 with the 5, multiply the infinity, which I now pretend is just a normal number, with the 1. And then I would sum all of these numbers up, and that would be the value of my inner product. Now, today we're going to do it differently. Namely, we're going to take not the product but the sum, because we replaced the product by the summation. So if I replace the product with the sum, what I get is 7, 7, 6, and infinity. And now, rather than summing over these as I would do normally, I take the min over them, which is 6. And this is the 6 that I put into my matrix on the right-hand side. Okay? And we can now repeat this exercise for all elements of this symmetric matrix if it's an undirected graph. But let's see what has happened here. So I'm just going to copy this result. All right, so this to the right hand side was the one hop solution. Now we have the two hop solution. In particular, we found that in one hop, the cheapest way to go from A to B, well, the cheapest cost was 7. But if I'm willing to do 2 hops, well, then the cheapest cost is 1 plus 5 for a total cost of 6. And this is what we have just computed. And I've highlighted in yellow all the places where there were changes between the best one hop solution and the best solution with up to 2 hops. In particular, let's say to go from A to D within a single hop, well, there is no edge from A to D, so the associated cost was infinity. But this time I find that actually there is a path, a lowest or cheapest path with a cost of 3. And well, note that there would also be a 2-hop path with a cost of 8, but cleverly we have found the cost of the lowest or the cheapest of these paths. And something else which was updated was the connection from B to C. So the single hop connection between B and C had a cost of 5, but if we're willing to make up to 2 hops, we find that it costs 3 units, as we have just found. All right, so this is the costs that we found when using up to 2 hops. And how did we do it? Well, we took this matrix, which had the edge costs, and we made this generalized multiplication of the matrix with itself. And the kind of matrix multiplication we did here was a min-sum matrix multiplication. And well, I find this totally great. Yeah? So what we have done is we are looking here in this formula. What we're doing is we're asking for the cost of the cheapest path from I to K and the cost of the cheapest path from K to J. But now we don't know which is the best intermediate node K, so we do a minimization here over all K. This is in traditional computer science would be the Floyd Warshall algorithm, and we here have a matrix formulation of it. And well, we can do the same thing once more. So I can now take this result. I have copied the result here. I have multiplied once more with this matrix holding the costs of single hop connections, and we get a new result which is the cheapest cost of any path with up to 3 hops. And I've again highlighted in yellow where there has been a change. Actually, if we look at this closely, by going from 1 hop to 2 hops, there were many changes. We have a lot of yellow. By going from 2 to 3 hops, actually only one entry changed. Namely, previously, the cost for going from A to B was 6. That was the cheapest cost, the cheapest path by using at most 2 hops. So 1 plus 5 is 6. But if we're willing to go by up to 3 hops, we find a cheaper path with a total cost of 4, which is this total cost of 4, which is what you see here. All right, and if we now do it another time, well, it will turn out that the matrix of costs no longer changes. This was here, well, true, because in a graph with 4 nodes, the longest path that you can have between any nodes is 3, so 3 is enough. But depending on the graph, you might also have this kind of convergence early on, when you have disconnected components, for example. So we observe closure, meaning if I keep multiplying this matrix with itself, at some point the result no longer changes. Good. So we have seen how to compute the all pairs, the conventional idea of what is the shortest path, by using a generalized matrix product. Do you have any questions about this? Okay, so we've been using this funny kind of matrix multiplication, and we found that it gave us the shortest path. Now, if you remember the kind of update rules that we used in this generalized single source or generalized Dijkstra's algorithm, sometimes we were interested in the widest path, where the cost of a path is given by a single most expensive edge. And it turns out that we can also just use some weird kind of matrix product here, where the sum is replaced by min and where the multiplication is replaced by a max. Or you see the formula on the left-hand side. So, for example, I'm looking at the widest or the minimax path from I to k, at the minimax path cost from k to j, and then the total cost of going from I to j via k is going to be given by the bigger of the two. But there are many possible intermediate nodes k, and now we're looking for the one where this maximal cost is as low as possible, hence minimax path. And yeah, maybe we can do one worked example. So I'm going to look at this element here. So I'm considering this row and this column. 0, 7, 1, infinity, and infinity 1, 2, 0. Now I'm going to take the max of the two, which is infinity, 7, 2, and infinity. And now I'm going to take the min of all of that. The minimum is 2, hence this is why there is a 2 up in this corner. We can do the same for all elements. Let's look at it in terms of the graph. So the widest bottleneck path from A to D, or excuse me, the minimax path from A to D is this one with a cost of 2, because 2 is the most expensive edge. that we encounter along this path. Okay, so that makes sense. And this gives us the widest bottleneck path with a length of up to 2 units. And well, if we're allowing ourselves up to 3 hops, we do not find anything better. But let's look at the connection between A and B. If we allow ourselves up to 2 hops, then the minimax path has a cost of 5, as you can see in the 2-hop result matrix. But if we allow ourselves 3 hops, then the widest bottleneck path is this one with a cost of 2, because 2 is the most expensive edge along that path. And again, if we did multiply in this general sense, in this minimax sense, this matrix with the cost matrix, the result would no longer change. All right? And so it means for matrix product with this funny convention, I find the minimax paths. And let's do the final example, existence of a path. I have this time replaced the costs here by statements of true or false. True means we have an edge, false means we don't have an edge. And at this time, we replace the product in our conventional operation with an AND. That means a path exists only if its first half exists and its second half exists. But if I'm considering multiple paths, it is sufficient if just one of these paths exists for I and j to be connected at all. And you see here that already after 2 hops, we find that everything is connected. So we have this convergence or this closure here a little bit earlier. All right. Final comment here. How can we make this faster? If I am interested not just in the best paths with up to k hops, but if I'm just interested in the best path overall, then I have to multiply this matrix, the cost matrix with itself, n-1 times for n nodes. And well, I could do that by saying, all right, I take A and I multiply, I've called this cost matrix A now, and I multiply it again with A, and I multiply it again with A, and so on. And I will do this for a total of n-1 times. But it is cheaper if we do it as sketched on the left-hand side. So we first build this matrix A squared, where now the product is in this generalized sense, and when I say squared, it's also in this generalized sense. So we say A squared equals A times A, and then A to the 4th power is A squared times A squared, and so on. And in that case, we need only logarithm of n matrix multiplications. Also, you will know that there are certain tricks. So naive matrix multiplication has a computational complexity of n to the 3rd, and using Strasser's or Winograd's algorithm for particular kinds of matrices, this can be done faster. So that's a trick that always applies. Or a really nice trick is also to use approximations. So that makes sense in some of the semi-rings to not multiply the entire matrix with the entire matrix, but to multiply only randomly selected rows with their transposed columns. And that has also been studied, depending on how big this randomized subset is, what kind of approximation quality you're going to get. This is the work of Uri Zwick in particular. Okay, but what's the big picture? Big picture is that we have found all kinds of interesting distances. The standard shortest path distance, the minimax path distance, or the existence of paths. And I have not shown it, but you can do this for other definitions, for yet further definitions of what a short path is. So this all pairs shortest path problem can be formulated in terms of generalized matrix products. And well, to me, that learning about this was a really, one of these light bulb moments, which, I enjoyed a lot, because it's such a simple and such a generic scheme to address many, many problems, to address the many instances where we do have shortest path problems in computer vision. Now, a disclaimer, this is all pairs shortest path. Oftentimes, you will not be able to afford even storing this all pairs matrix. So if you have 1,000,000 pixels in your image, then the all pairs matrix would be 1,000,000 times 1,000,000, and that's likely too large for your computer. So we cannot use all pairs on the pixel level usually. Well, we can do it on patches, but not on whole images. But it does work on coarsened graphs of superpixels, and the like. All right.